Hi students, in this video we're going to go over section 5.2, functions. So our goal for this video is to discuss functions in more detail. This was the definition we had in the last section for a function. So just as a reminder, we're going to let x and y be sets, and a function f from x to y is a relation from x to y that satisfies these two properties. The domain of the function is equal to set x, and for each x in set x, there is exactly one y in y, such that the ordered pair x comma y is an element of the function. And set x is called your domain, and the set of elements y here, such that x and y, that ordered pair is in the function, is called your range for the function. And you can denote it this way. So example 1, we're going to let x be the elements, or the set of elements a, b, and c, and y is a set of elements 1, 2, 3, and 4. We're going to define a function from x to y by this arrow diagram here. So this arrow diagram, that represents a function. What is the domain of f? And it's going to be all of set x. So I'm going to just write that on the next slide. The domain is x, which is the set containing the elements a, b, and c. And for part b, we want to figure out what's f of a, what's f of b, and what's f of c. So just like the regular function notation we've used before. So we're trying to find f of a, f of b, and f of c. And we're just going to use the arrow diagram to help us with that. So a here goes to 2. So 2 is the f of a. And for b, b is paired with 4, so 4 for f of b. And then what's f of c? Also 2. And then for part c, what is the range of the function? So the range of the function is not going to be, not necessarily the whole set y, it's just which elements in y are paired with elements in x, set x. So it's just going to be the 2 and the 4, not the 1 and not the 3. So the range is the set containing 2 and 4. And then for D, represent F as a set of ordered pairs. So A goes to 2, B to 4, C to 2. So F here as a set of ordered pairs, you're going to have A comma 2, B comma 4, and C comma 2. A little bit more with your function. Given an element y in set y, there may exist elements in x with y as their image. If f of x equals y, then x is called the inverse image of y. So if you have an ordered pair, let's do x comma y, and that's an ordered pair in the function f. Y is the image of x, and x is the inverse image of y. That's how you're going to think of it. So some new terminology here. So let's do an example to see how this works. So we have the same arrow diagram, and we have the same sets x and y. So now for part A, we want to know, is C an inverse image of 4? 4, B and 4 are actually an ordered pair. 4 has nothing to do with C. So your answer for A, part A, is no. Is A an inverse image of 2? A here, yes. A actually has 2 inverse images, A and C. So we'll answer yes for part B. And then C. Find the inverse images of 4, 3, and 2. Okay. So in that order, 4 has the inverse image B. So I'm going to say the inverse image of 4 equals b. I'm using set notation there. And then we're going to do the inverse image for 3. 3 is not actually used. The 3 and the y is not used, so it doesn't have an inverse image. So you're going to write inverse image of 3 is the empty set. You can use either of those notations. And then the inverse image of 2 is going to be the A and the C. So the inverse image of 2 is the set containing A and C. Example 3, we're going to define a function S which maps positive integers to other positive integers as follows. For each positive integer n, S of n is going to be equal to the sum of the positive divisors of n. So for part A, S of 12, you look at 12, you're going to list all the positive divisors of 12. So like 1, 2, 3, 4, 6, and 12. And then you're going to sum them. So you get 28. And then for part B, S of 19, the positive divisors are just going to be 1 in itself, 1 and 19. So when you sum them, we'll get 20 for that. Arrow diagrams. So if x and y are finite sets, you can define a function from x to y by drawing an arrow from each element in x to the corresponding element in y. So we saw this in the previous section. The arrow diagram defines a function if 1, every element of x has an arrow coming out of it, and 2, no element x has 2 arrows coming out of it that point to 2 different elements of y. So for example 4, determine which of the following arrow diagrams define functions from x to y, and just explain. So for part A, this would be a function. Part A is a function. This is R here. R is a function. And you can see all the elements here are used. They all have an arrow coming out of them, but only one arrow is coming out of each of those. And then part B, this is not a function because of this issue right here. So no, S here, S is not a function. The element A in domain X is related to 2 elements in set Y. So I'm going to say the element A in domain X is related to both 1 and 2. That's why it's not a function. Part C, we have a relation T here. And if we look at it, all of these are used. All the elements in set X, the domain, are used, and they're used only one time each, right? So each of these have an arrow coming out of them, and they only have exactly one arrow coming out of them. So yes, T is a function. And then part D, does that represent a function? So we have V here. And if we look at our set X, the domain, not all of them are being used. Not all the elements are being used. V does not have an arrow coming out of it. It's not related to anything over here in Y. So no. V is not a function. And I'll just put down the element B in domain X is not related to any element and y. Here we have a theorem that's a test for function equality. So if x relates elements in x to elements in y, and g relates elements in x to elements in y, if these are both functions, then f is equal to g if and only if f of x is equal to g of x for all x in set x. So basically these here, the range for f and g are the same for all x. So for example 5, we're going to define a function f and a function g that relates real numbers to other real numbers. Goes from real numbers to real numbers. F here is the function that's the absolute value of x for all x in the set of real numbers. And g of x is equal to the square root of x squared for all x in the set of real numbers. Are these equal to each other? So will f of x and g of x be equal to each other for all real numbers, for all x that you plug in? And just think of that. Think about that for a second. Right? So if you plug in a positive number for x here or here, you'll get the same output, right? Let's just look at like positive 4, for example. And this is not a proof or anything down here. I'm just kind of seeing how it would work if I plugged some numbers in. If I plugged in 0, I would get 0 for both of these. And then if I plugged in a negative number, so negative 2, I'll get positive 2 out here. And it was g. Since I'm squaring it, I'm making it positive, but then I'm doing the square root, so I'm going to have positive 2 come out. So yeah, these are going to be equal. And then checking whether a function is well defined. So sometimes a function defined by a rule is not really a function at all. So if a function is not well defined, then it actually wasn't a function in the first place. So a well-defined function satisfies those two conditions of being a function, which we've already discussed. So let's look at example 6 and just kind of see what something would look like if it's not a function. So suppose someone tries to define a function this way. So we have h, and it goes from rational numbers, relates rational numbers to other rational numbers by this rule here. So it's saying if you plugged in this m over n into your function, then what's coming out of it is m squared over n for all integers m and n with n not equal to 0. And we're just going to explain why this function is not well defined, so why it's really not a function to begin with. So if h were a function, or were well defined, then h of 1/2 would have to be equal to h of 2/4, right? And this is because 1/2 is equal to 2/4. But if you plug the 1/2 into the function, it's telling us to square whatever the number in the numerator is, and don't do anything with the denominator. So you get 1/2 when you plug 1/2 in. And when you plug in 2/4, you're going to have 2 squared over 4. Well, that's just 1. So since 1/2 does not equal 1, then h of 1/2 doesn't equal h of 2/4, even though 1/2 is equal to 2/4. Thus, h is not well defined. It's like if you were doing some type of arrow diagram. So we have a Q here, we have Q, you have H, right? Basically, you have a 1/2, which is your 2/4, and it's going to boast a 1/2 and a 1. That's what's happening. So you have basically the same element X in the domain that's mapping to two different elements. Definition for functions acting on sets. So if F here maps elements from X to Y, if that's a function, and A is a subset of X and C is a subset of Y, then F of A is going to be equal to the set of elements Y in set Y, such that Y is equal to F of X for some X in set A. And then this is going to be your inverse function of C. It's going to be equal to your elements X in set X, such that F of X is an element of set C. F of A is called the image of A, and F inverse C is called the inverse image of C. Example 7. So set X contains the elements 1, 2, 3, and 4. Set Y contains the elements A, B, C, D, and E. And we're going to define as follows. So G of 1 is equal to A, G of 2 is equal to A, G of 3 is equal to B, and G of 4 is equal to C. The first thing we're going to do is draw an arrow diagram for G. So for part A, we have set X, set Y, we have G here, going from X to Y. X had 1, 2, 3, and 4 in it, and Y has A, B, C, D, and E in it. All right, so G of 1 is equal to A. So 1 is related to A. We have G of 2 is related to A. So 2 related to A. G of 3 equals B. So 3 is related to B. And G of 4 is equal to C. So 4 is related to C. Okay, that's part A. And then we're going to let A here, capital A, be the set containing elements 2 and 3. C is just a set containing the element lowercase a. And D is the set containing the elements B, C, and D. We're going to find each of these here. So what is G of A? So for part B, G of A. So basically, set A contains 2 and 3. So you can think of it this way. So basically, you're thinking about plugging in 2 and also 3 into the function G and seeing what you get as the output. So when you plug in 2 and 3, the outputs are A and B. And use set notation here. For part C, we're plugging in set X. Well, set X is just the whole domain. That's everything here. 1, 2, 3, and 4. So the outputs are going to be A, B, and C, which is going to be your range. That is the range. And then D, inverse. Let's see, D is going to go here, and it's the inverse function. We're plugging C in. But C was, what was C? C is just a set containing A. Here's A. This has 2 inverse images, 1 and 2. You have 1 and 2 there. Use set notation. And then inverse for G. Again. But this time we're putting in set D, which is B, C, and D. Okay. B, C, and D. B has the inverse image 3. C has inverse image 4. D doesn't have one, so we're just going to have 3 and 4 in the set. And then last part, F, we're doing G inverse of Y. So that's all of these here. So all of these are going to be in a set. Those are all the inverse images of the set Y. And it's just the domain, basically. And that's it. So we're done with this section 5.2. Try the homework, and I'll see you in the next video.